Okay, well, welcome everybody to this the second webinar in the Unforgettable Research Services series. In this webinar, what I'm planning to do is to focus on privacy-preserving data analysis, and particularly of personal data. So, obviously, as you start to deal with data which has a much more is much more sensitive, you need to think more carefully about how you go about doing your data analysis and what tools you use. And so, I'm going to be focused today on a solution that we've been working on in the company called Private, which is new computing language. And I'll go through why we've taken the somewhat extreme step of developing a new language in order to deal with privacy concerns. I just want to let you know that we have two people from the company here, Ben Stone and Michael Diamond. They'll be in the chat room and monitoring that. So if you have questions as we go along, feel free to ask those in chat. For those of you who attended the first session, this one's going to be a significant step up in terms of the technical component. So it may be that this you might find some of the material fairly challenging. So feel free to use the chat, or if Ben and Michael see some common threads in there, they might let me know, and I can stop and address those questions. Okay, so as I was saying, as we move towards data sets that contain more personal information, we have to be conscious of the fact that there's a kind of a yin and a yang to this enterprise. So last time I talked a lot about the promise of big data analyses, and how in my opinion I think they will be a kind of complete revolution in the way we do psychological experimentation and data collection, certainly, just because they have the capacity to actually get at the people's lives at a level of detail where we're getting what's happening in the real life, and we're getting enough data about an individual to have some reasonable chance of predicting how they're thinking, what their behaviour is likely to be. But of course, the flip side of that is that it is very personal data, and so in some sense its usefulness is directly related to the fact that it's very personal data, and so therefore the privacy concerns become much more acute than they would be with other data. The other thing I would say is that if you look at the computational privacy area and some of the work that's being done there at the moment, it seems that even a lot of data sets that we would have once considered perfectly safe, they've discovered ways of being able to analyses that are able to identify people even in this data. So recently we've been doing a big survey on COVID, a cross-cultural survey on people's approaches to contact tracing technologies in particular. And so this is just a survey in the normal sense, and we have it balanced by things like age and gender, and in Australia, in the case for Australia, we had the state of residence. But we didn't have in the release set that we originally put out, we didn't have anything like GPS coordinates or auditory or accelerometry or any of those more dense kinds of data. Nonetheless, one of the computational privacy guys came back to us and said, well, this, even at that level, if you've got, gender and state and age, with a little bit of additional information off the internet, I can still identify some of the people in your sample. So even the samples and methods we might have thought were perfectly safe turns out is not the case by the time, because of all of the additional information that exists on the internet that people can use in collaboration with the data that we might release in order to be able to identify our participants. So, so I think, you know, it's acutely important when you're using sensitive data, but I think just overall we've been a little bit blasé about the way that we've handled data, and that of course has been accelerated by the open science movement, where the push has been to put these data sets online, and of course as soon as you do that, they're open to anyone who might want to try to exploit them. And of course that has happened in various different ways. And so, so for instance, there was the famous Cambridge Analytica scandal where 87 million Facebook profiles were taken and were potentially used to influence the US presidential election. So that's a clear case where there's been a breach. The kind of key player in this was a researcher called Alexander Kogan. He's a social psychologist that studies personality. And what I want to emphasize is that Kogan was a research associate at Cambridge University. And so, you know, had at least the appearance of being a perfectly legitimate researcher, was not, was using the Facebook system under that assumption. And there was no hack in this case. So it wasn't that there was some kind of security breach and someone got in. In this case, it was a perfectly legitimate person. And to this day, Kogan insists upon his innocence. So he still doesn't see anything wrong with what he did. So so I think that's a very important lesson in that different people have different understandings about what's appropriate, and we can't just rely on our legal frameworks or anything like that in order to ensure that there aren't breaches. And that, I guess, is underpinned by one of the key aspects of data, and that's that it can be copied, and it can be copied very readily. So this is a graph showing the relationship of Kogan to the other major players in the Cambridge Analytica scandal, so Alexander Nix and Steve Bannon. So I'm not going to go through this slide in any detail, but essentially what's happening here is that data, once it's been collected, is making its way to multiple different places, some of which may not be appropriate. And there have been efforts to try to audit different people's machines and make sure all of that data was deleted, but how would you ever know? It's always possible that that data set still exists. Once the data is out, it's very hard to get back into the bottle, if not impossible. So, so we really need to think very seriously about the methods that we use in our data analysis, and not just rely on people's goodwill and common understandings to make these things work. This is just making that point again, that in this scandal, there was no hack. So with the Facebook app, what happens is that you put the app up, someone who uses the app was able to consent not only for the use of their data, but also for all of their friends' data. And that's how it grew to be such a huge data set so rapidly. So yeah, I don't think Facebook will do that again, but nonetheless, this kind of dynamic exists every time we start to develop a team of researchers who are working with data. And for many of us, that team gets bigger and bigger and bigger. And every time you add someone, the chances of a breach increase. Now, what I want to argue is that the current methods that we use for data analysis really just have no processes or no ways of maintaining people's privacy. So we're essentially working in a world at the moment where we assume the good faith of all of the researchers who have access to the data. So you can kind of see this. I've given a kind of joke example here, but if you've got someone's emails, for instance, then you can search them and you can find out information about specific individuals. And that as long as that data exists, everybody who who can do, who has access, can do that very readily. And none of our major languages do anything to stop that from happening. So, regardless of whether you're working in R or Python or MATLAB, you always have complete access to all of the data. And so necessarily that's problematic if you want to protect people's privacy. So, and I would argue it's very difficult to retrofit existing languages because they all work under the assumption that you'll have direct access to that data. And in particular, it's not, even if you could restrict access to the specific underlying data set, if you have a kind of deterministic language where you can calculate some kind of function based on deterministic function based on that language, on the data, it's always possible to reconstruct people's private information. And so, you need to build in certain kinds of probabilistic mechanisms for there to be any protection at all. And none of those languages have those probabilistic mechanisms built into their underlying structure. So that's why we embarked upon developing the private language. And so that's the name of the language as well as what it tries to achieve. And there are a number of aspects of private that are designed to ensure people's privacy. So the first one is that it tightly couples the data and the analysis. So if you think about it, right, as soon as you give people the capacity to download the data, the cause is already lost, right? So you can't prevent breaches while they have the ability to download data. And so what private does is it assumes that the data is never downloaded, that the analysis happens on the machines that are provided by whoever collected the data. And then what you do is you provide those analyses, they get run on the data, you get results back from those analyses, but you never get access to the data itself. And I think any privacy preserving language has to operate in that fashion because, as I said before, as soon as you allow the data to be copied, there's nothing stopping it from being copied, many, many times. Now, the other thing that it does is that before any result is released, it's subjected to a set of tests that determine whether it should be released or not. So in some cases, so in all of these environments, we know which of the participant data, so we can figure out the set of dependencies that exist between a certain analysis and that data. And we can analyze those to say, well, is this a result that could be released? So if it only relies on information that the programmer has put in themselves, well, then it's fine, right? Because they've already got access to that information. But if it relies on that private information, then there's always a possibility it could be a breach. If it's a deterministic relationship between that private information and the result, then it's always a breach possibility. And so in the language, it always prevents you from releasing that information. But if it's a probabilistic relationship between the data and the result, then it depends. Then it depends on to what extent that probabilistic result that you've produced is sensitive to the data of any given individual. And so what the language does is it builds those tests in at the base level so that the result doesn't get released unless those tests are passed. Private is a probabilistic and deterministic language, and what it does is it tries to take advantage of people's already existing knowledge of Python and also the bugs, JAGs, Stan family of languages. So Python's a deterministic language, bugs, JAGs, and Stan are developed for defining probabilistic models, Bayesian probabilistic models. And so what it does is it uses syntax from both of these languages and merges them together to give you a kind of comprehensive platform for dealing with the language. like bugs and JAGs, it is a declarative language, not a procedural language. So many of the languages you might be familiar with, like Python or R or MATLAB, are procedural languages. One statement is executed, it changes the state of the program, and then another statement is executed, that changes the state of the program, and so forth. So everything kind of happens conceptually in sequence. In declarative languages, what you do is you define what the results of your computation are supposed to be, and then it's up to the program to figure out how to actually go about computing those results. And so creating a declarative language like this is the way languages like bugs and JAGs work. Doing that means is a more natural way of defining a mathematical model. And it also has significant advantages for privacy assessment. So in particular, it's easier to analyze privacy because for a given program, the privacy of a given variable is always the same. So in a procedural language, it's possible that as you go through from step to step, the privacy sensitivity of a result for a given variable could change, right? So you might start off just initializing the variable, which has no privacy implications. But then in the subsequent step, you might then change the value of that variable in order to, on the basis of some kind of information that came out of private data. And so therefore, the privacy status of any given variable can change as a function of state in a procedural language. But that's not true in a declarative language. Once you've defined the program, you also define the privacy status of the variable. And so that makes it much easier to create the appropriate text, because you don't have to worry about all possible ways in which the procedural program might fork. So that's important. But unlike declarative languages like bugs and JAGs, where you have to provide the whole program in one go, private actually allows for incremental definition, and you'll see this in the examples that I give. So we can continue to change the definition of the analysis that we're doing, and that will continually update the model that it's trying to compute. And the language itself knows when that's happening and knows which pieces of which variables need to be recomputed in order to meet the current definition of the analysis. Another big advantage of making it declarative is that this makes parallelization a lot easier. So a lot of these analyses that we're starting to do now are very large and therefore need to be parallelized because of the sheer time it takes to compute. And one of the advantages of a declarative language is that, again, it makes it easier for you to figure out what the dependencies are and to automatically parallelize. So I'll demonstrate that in a little bit. We're using a number of different technologies. These might be familiar to some of you. So the underlying engine that does the probabilistic calculations is called PyMC3. We're using Redis, Dask, Arpeggio, S3, and Seaborn. So don't worry about it if you don't know what those are, but if you do, those are the technologies that we're using. And private is an open source project. Okay, so just to reiterate that point, for any serious privacy preserving language, you can't just download the data onto your hard drive and start analyzing it. And so in private, what happens is you log into the system. So there can be multiple systems, but the one we're using is Unforgettable. And so you log into the system, and then it provides the environment, the shell that you use to interact with the data. And the data is just there from the outset. So depending on the environment that you log into, that will be different data sets. But there's no loading the data in or anything like that. The data already exists as a special variable called events. that is in the current context as soon as you log in. And so that eliminates that step of you having to actually load in the data and set up the environments and so forth. The other thing, of course, is that when you're developing a language like this, you have to be very careful about the nature of the environment that that you're operating in, because if you allow people just to define arbitrary functions, they could define those functions in ways that try to circumvent your underlying privacy control. And so, so what in the private kind of ecosystem, it's a kind of defined environment, and you have to work within that because all of those functions have been tested or have been designed to ensure that they don't create any exploits. Okay, so let's talk a little bit about how what a private program looks like. So in a JAGS or a STAN program, what would happen is you would actually have to develop you'd have to know two different languages. So you'd have to know R or Python or MATLAB, and you would use that language in order to get your data into the appropriate format. And then then you would call from within that language, you would call a JAGS or STAN program that you also coded, and that would then run on that data and would return its results to R or Python, and then you would do all of your post-processing on those results in R or Python. So as the current state of the art, it's creating these kind of probabilistic programs is quite difficult, because you essentially need to know at least two different languages in order to be able to make this kind of ecosystem work. So in private, we've tried to pull that up or eliminate that kind of difficulty and embed everything within the language itself. So that means we've got both probabilistic primitives as well as deterministic primitives. So in here you can see the very first statement I've got here is L is equal to Bernoulli 0.3, 100. So what this is doing, so the equals here indicates that this is a deterministic definition. And so even though this is going to be, we're going to create this data randomly, once it's created, that's going to be just the fixed data. It's not going to change. Okay. So so we're going to define this as a Bernoulli. So Bernoulli is basically just a coin flip distribution. So what this line is saying is create a variable which has 100 values in it, and each of those values will be either a 0 or a 1, and the probability of a 1 will be 0.3. Okay, so if you look down here, we can do SV. SV stands for show variables, and so here's the variable L, here's the code that generated it, and here's the kind of representation of its values. So obviously there are a lot of values in L, so in SV we don't print them all out, but you can print them all out if you want, and that's just by typing in the L, and here you can see all of the values that were generated for L. So I'm going to use this as a kind of representation of our data in the first instance. Now notice here we can see everything, right? We can see all of this data, and we could create, calculate means and standard deviations and all of those kinds of things on it. And that's because we defined it, right? So as the programmers here, this is a public variable because we defined it. This would not be the case if it was private data. So this is an example of a deterministic definition. So we're saying L is equal to this Bernoulli. Now, in addition, though, we want to be able to set up probabilistic models, and we're going to use the kind of structure or terminology or syntax that is common in probabilistic languages like STAN and JAGS and bugs. And to define a probabilistic variable, we're going to use the tilde. So here we're saying that we've got this data, so we know, because we defined it, we know that there was this underlying rate of 0.3, which was what generated the data. But now we're going to say, let's suppose we didn't know what that was, and we were actually trying to estimate that value. So we wanted to find out, what is that 0.3? We don't know. It's a variable out there in the world now, and how do we go about estimating it? So we're going to set up a definition. L is distributed as a Bernoulli, and with some rate parameter R here. So this is the unknown parameter that we want to find. Okay, so now you'll notice L has both a deterministic and a probabilistic definition. So so here is the actual data. Here is the start of our model, okay, of what that data is. So we're saying we don't know what R is, but we're going to hypothesize that it's that L is distributed as a Bernoulli. Now, we happen to know that that's exactly correct because we actually defined the data ourselves, but in reality, we wouldn't know that if that was the right definition. But that would be our model. That would be the assumption that we're making to try to understand this data. Now, in the Bayesian sense, right, this is not enough by itself. So this actually defines what's called the likelihood. So this is how does the variable R, the rate, how does that relate to the data? Okay, so that's the first piece that you need for the model. But the second piece that you need for the model is the prior. Okay, so here what we're saying is that this R parameter is distributed as a uniform distribution with that goes from 0 to 1. So we're saying that's kind of defining our knowledge. So to begin with, we're saying we don't know. The R parameter could be anywhere between 0 and 1. And we do know it's a rate parameter, though. It has to be between 0 and 1. But we don't know where it is between there. But we're going to just assume from the outset, our kind of initial knowledge before we see the data, is that it's somewhere between there and that all possibilities are equally likely. Now, once we've done that, we've now defined our likelihood and we've defined our prior. And so when we've done that, now everything that we need in order to compute the R, to estimate what R would be, we have. So we need a likelihood, we need a prior for all of our variables. Once we've got that, we can calculate we can go ahead and sample. So now, in most cases, in procedural languages like R and Python and so forth, you would actually call a function which would do the sampling for you. In private, what happens is that as soon as it realizes that that you have all of the definitions that you need, it automatically starts sampling. So down here, we've done our SV again, which means show the variables. And you can see we've got all of the variables we've defined. We've got two definitions for L now, the deterministic one and the probabilistic one, and we've got our prior for R. And as soon as we do that, it starts computing. So what it's doing underneath the hood is it's running a Markov chain Monte Carlo simulation. And what it's going to come out with is a whole series of guesses, essentially, at what R might be. And but that takes some time, and so it's going through and at this point doing that computing. And all of that just happens automagically. So there's no need for you to tell it to start computing. It will just do that as soon as all of the requisite definitions are in place. Now, in the meantime, while it's doing that, you can continue interacting with the shell. So you could say mean R is equal to the mean of R. You can say standard R is equal to the standard deviation of R. And you can add those definitions whenever you like. Now, in this case, right, we don't need to, adding these definitions won't change what R would be. So they are all derivative upon R. They don't change what R would be. And so therefore, the computation just continues And when that finishes, it will automatically update mean R and standard R. So you've said, you've defined it, saying mean R is equal to this, standard R is equal to this. The language knows that, and so it can't actually update those variables right now, but as soon as it can, it will realize that and it will go and update those variables. So one of the big advantages of this is that once you've got a program, you don't have to worry about, have I rerun all of the sections of the code I need to make sure everything's up to date. The language handles all of that for you. And one of my contentions is that a lot of times when people are analyzing data, they forget, they think they make a change to a parameter somewhere, and they forget to actually rerun all of the code that's required in order to make sure the variables are up to date. And so, so therefore, often incorrect results that we might see might just be purely a function of that. With private, that's not possible because the language itself handles updating all of the variables. Now, I said before that mean R and standard R are derivative on the variable R, and therefore they can be added and they'll just be updated as soon as R is computed. If we had changed one of the definitions, however, that did change R, then what would happen is the sampler would actually restart. So the language constantly works to make sure that all the variables you see are consistent with whatever the definition is at that point in time. Okay, so now let's suppose the sampler is done. And so down here, you can see we've got R, the definition of R down here. And now we've got a whole set of samples in here. And you can see that they're, in the ballpark of 3. So here's our mean, and that's 0.355. So not exactly 3. So that's the mean of all of these samples is 0.355. So it's not exactly 3, but it's in that ballpark. And here you can see the standard deviation. So that's how we go about estimating parameters from data. Okay, so this is just making the point that I was before. So now let's say we change one of the definitions. So L is equal to Bernoulli 0.9100. So now we've changed the underlying data. It's a new program because we've changed what the data is, the samples for the data are. And so then what happens is that the language realizes that, and it goes through and it resamples those values. And so now you can see the samples are different, the mean is different, and standard deviation is different. So you didn't have to recalculate anything. All you do is change that definition, and the language knows that requires these changes. Plotting works similarly. So we create a variable. In this case, rplot is equal to a distribution plot. This plot of R. You can see down here we've got that plot, and so rplot just slots in as another variable in the same way as any other variable in the language. And so it's just got a PNG image here, and that's what that image would look like. And so there's a whole library of graphics routines that you can use. And similarly, as to all of the other variables, if you update a definition, so now we've changed the data to have a rate of 0.5, everything else gets updated at the same time. Okay, looks like everything else except my slide gets updated at the same time. So this should have been 0.5 here, and this should have been the samples. Would have been updated, and if you're in the real language, that would have happened. But the point that I wanted to make here is that the graph has updated, and so now you can see we've got samples that are in the vicinity of 0.5. So even the graphics are being updated dynamically. So you never have a graph that's inconsistent with your program. Okay, so Other things that you can do, when you have these Markov chain Monte Carlo methods, there are a number of different parameters that as you become a more advanced user, you need to be able to manipulate. So I said before that a set of samples were constructed from the underlying sampler, so samples of R. How many? Well, we can change that. So by default, it'll do 1,000 samples and it'll do what's called 2 chains. So in Markov chain Monte Carlo, if we look over here, we can say, here's their samples. And so what it does is it calculates the first sample and it calculates another sample based on the first one, calculates another sample based on the second one, and so forth. So it gets a whole series of these samples. Now, what we want to be able to do is to test to what extent has that chain of samples converged. Have we actually got to the appropriate posterior set of samples for that model, given the data and the priors? And so what we often do is we'll run multiple chains and see to what extent, and they start from different places, and we feel comfortable saying that we've got the right output set of samples if those 2 chains converge, i.e. if they look like they're on top of each other. So in this case, we had 2 chains, and that was set by the number of chains variable. And you can see that they are lying very much on top of each other, right? They're not exactly the same, but they're very similar to each other. So that gives us confidence that we really do have a proper set of samples from this posterior. But we can control that through the number of samples, number of chains. And also typically what we do is we remove a set of samples from the start called the burn-in set. And for our different algorithms, there are different ways of doing that. And so those are called tuning samples. And so we get rid of those and we can vary how many of those we get rid of by changing this number of tuning samples. So that so those are some of gives you some control over the sampler, which is necessary for more advanced users. The other thing we can do is we can test whether create tests of that convergence. And so one common test is given by Gelman and Rubin and called R hat. And so what you're looking for is the R hat to be close to 1, and then you know that you've actually got a set of chains that has converged. And so here you can see we're very close to 1, so we're in good shape. So this R hat is just a standard variable in the language. You just type that and you can see what it is for all of the different variables that have been defined. We also have methods for assessing model fit or doing model selection. I won't go into these in any detail, but there's built-in primitives for the widely acceptable information criterion, WAIC. You can calculate the effective sample size is automatically calculated, and there's also a method for leave one out cross-validation. So all of those are built into the underlying structure, and you can just query those in order to find out more about what was happening with the sample. So I said before that there was a lot of parallelism going on. So this just gives you an idea about some of that. So let's say we've got, we're trying to get samples from 2 distributions, 2 Gumbel distributions in this case. So one for T, one for T2. Notice these don't depend upon each other. So once we know N, these 2 can be calculated in parallel. And we do an SV here, and you can see, in fact, they are being calculated in parallel. SJ stands for show jobs. Here we can see the total number of jobs, and we've got 2 of those computes, and these are the variables being computed. So what's happened is the private's being deployed across a cluster, and different machines are being used to run these different computations. But you don't need to know about that in order to use the language. The language just figures all of that out for itself. There are a bunch of built-ins that you can use, and also a bunch of probabilistic built-ins that you can use. Okay, so I want to quickly finish off by giving you a sense of, well, why is it called private? And the key here is what happens when you start to look at data sources that are private, that have sensitive information in them. And as I mentioned, there is this variable called events. And if you type in events, it will just tell you that is private. It will not allow you to see what's inside that variable. Okay. And so that's the key to the exercise. So for purposes of demonstration, we've come up with some mock data. So this is not real people's data, but just some mock data that we've created. And so that's in a variable called demo events. And it looks like this. So this is just one record. So this would be data that comes out of off the Unforgettable app. So it has things like the number of kilometers you went, the latitude and longitude, battery level, has addresses, it has the time of the event, and a whole bunch of keywords. So were they, this is indicating they were on the street when this was happening, that it was raining, etc., etc. Okay, so lots and lots of data that's come off the Unforgettable app that we can analyze. Now, if we did this, so let's say we wanted to calculate the probability of rain. Okay, so rain, we're going to say it's either raining or it's not raining, and so we can go through here and calculate a variable called rained. And so rained is going to be like L in our previous examples, right? So it's going to be a big list of trues and falses, depending on whether for each of the events in demo events, which has a field that's weather, whether that event was, it was raining during that time. Okay, so we get false, 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 true, false, false, false. So we want to figure out, okay, is that, what's the rate at which it was raining for the events in our data set? So we're going to go through and do it exactly the same way as we did before. So we've got rained, we're going to define as a Bernoulli because it's like a coin flip. We want to know the rate underlying this. And we're going to set up the prior as a uniform. And now it goes away and it does computing just as it did before for our data that we created. We go through, we get the samples here of R, and we can calculate the mean of that. And you can see it's around about 0.33 is the mean. So that's our estimate of the rate. Now, that was all done with the variable demo events, which was a public variable. So that was just for demonstration purposes. What would happen if we were actually using events, which is how it would actually work if you were really doing this data analysis? Well, now what we would do is we'd define rained in the same way, but now we'd be defining it on the events variable, not on the demo events variable. And events is a private variable. And so what the language figures out is, because events is private, that means that anything that's derived from it in a deterministic fashion, like rain, will also be private, because that could allows a breach, right? So if this is private, then, and we've got a deterministic function of that variable, this could be a breach. And so now when we show this, you see we don't see what's underneath there. It tells us it's private. But we can go through and calculate our samples still the same way as we did before. So now we've got rained as a Bernoulli, R as a uniform, and it's gone through and it's doing the computation. Now, when it does that, again, this is all happening in parallel, and so we can do an SJ, and we can look at what's underneath, what processes are running. And you can see there are 11 jobs here, and it says there are 11 sampler jobs. So what it's actually doing is it's going through and it's running this, this underlying computation, but it doesn't do it just for the entire set. It does it for every subset of the data with one person missing. And so what we're going to do is we're going to say, okay, do we get effectively the same kind of set of samples regardless of which, if we have data that is missing one person? So if we take one person out and that changes the set of samples that we get significantly, we've got a problem, right? Because that means our samples are sensitive to that particular individual. But if we can go through all of the individuals and there's the samples that we get are not sensitive to removal of one person, then we're okay to release those samples. So that's what it's doing. So it starts off going through calculating all of the samples. At this point, you see this has changed to privacy unknown. So at this point, we've calculated all of the samples that we need, but we don't know at this point, it's going through and doing that sensitivity analysis. And that's what this manifold privacy jobs is doing. So there are 8 of those at this point in time on R. So it goes through, divvies those up to all different computers across the cluster, and then eventually comes back. And in this case, we find that it wasn't too sensitive. And so now it has released those samples. And so we can go through and calculate the mean. And in fact, that's exactly the same as what we got from demo data, because it's exactly the same data. And we're good, okay? However, it was possible that if one user really changed that, they would come back here and say, no, that's no good, that's too sensitive. So just to run through that algorithm, so here we have a random set of individuals who vary on different dimensions. And let's say we have some distributions that have been calculated on perhaps the amount of red in their outfit. So what we calculate the samples with all of the individuals included, and then we go through and calculate the distribution again for each subsample with one person removed. So when the first person's removed, we're just seeing the data of these people, we calculate the sample. Now we're seeing the data from these 3, we calculate the sample. We can see the data from these 3, and bingo, now the sample has changed quite dramatically. And when we do these 3, we see this, right? So this is the fact that this distribution does not look like that distribution. So what it is, when we have this person missing, it doesn't look like when we have everybody in. That says, okay, this is sensitive, okay? And so we could potentially release some important information about this, about that person if we gave out these samples. So we won't do that. Okay, so that's essentially the end. That's I guess a taster for how this works. And but obviously I've had to kind of whiz through, and there's a lot of details there that I can't cover in the context of a 1-hour presentation. But hopefully what you've got is a sense of just how we go about doing this privacy preserving computation and analysis. If you're interested in kind of learning more and getting more of a hands-on kind of approach to understanding private, we're running a workshop next, Thursday 2 weeks, I believe it is, so June 11th. And so please feel free to register for that or to turn up. And there I'll be going through and I'll be giving you all your own private shell to work with, and we'll be going through and doing some exercises in a kind of lockstep, so you get more of a sense of how this works if you were actually working with the data. And I guess what I want to do is just finish with some take-home messages. So I believe behavioural science is undergoing a revolution. I think this is going to make all the difference in terms of our ability to really understand what's going on in people's minds and to understand their behaviours. And it's really all underpinned by these big, dense data sets that allow us to understand predictive influence human action. But the current state of privacy preservation in data analysis languages is not even close to good enough. In fact, the vast majority of languages make no effort whatsoever to protect people's privacy. And that's, I think, something that's going to have to change, because as we've already seen, there've been multiple breaches of people's data. And as I pointed out in the Cambridge Analytica case, this is often from people who look perfectly reasonable. And in fact, you know, it may well be perfectly reasonable. They just have different expectations from what other people have. So, you know, as our project teams get bigger, as the nature of the data that we're operating with gets more sensitive, we're really going to have to change this, because this is going to just keep happening again and again unless we get a handle on this issue. So what I hope I've convinced you of is that private provides a mechanism by which individuals, enterprises, and institutions can really start to take privacy seriously in the way that they go about doing their data analysis. Okay, so that is it from me. So I might, well, I might just ask for questions at the moment. Does anyone have anything that they would like to ask? How here do I? Okay, let me go out. Okay, is there anything that people would like to? I know it's a lot of information to take in a very short period of time, so so I could absolutely appreciate why it might be difficult. Okay, so we've got so when we work with natural language, so Andre asked, when we work with natural language processing, is there any recommendation? Yeah, so so I guess it depends on what the purpose is. So if you're trying to do a generic, so private is really set up assuming you're trying to establish some kind of regularity across a population of people, which is the situation we're most commonly encountering in kind of psychological and behavioural science. So I guess the first thing to say is that if you're trying to make specific predictions for a given individual in a system that's designed to provide that information to the individual, then it's a little bit of a different situation. And in a lot of natural language processing, that's the case. However, if you're doing natural language processing because to extract regularities over people, then I think all of these kinds of issues that I'm talking about are just as pertinent there, and perhaps even more pertinent. So, but a lot of the time, right, the natural language processing that you're doing can be embodied in a set of underlying algorithms. But the result that you need doesn't necessarily need to come directly from those algorithms. So what you might do is create the result, so do what you would normally do in that natural language processing, but then you would put a probabilistic layer on top of any result that you're trying to get out of that. And then that probabilistic result would be subject to all the tests I was talking about. So so you can still do it, even if you have quite complicated underlying algorithms. That's not necessarily a problem, and they can all be just exactly the same as you already do. The difficulty only arises in terms of what is the data or what is the result that you're actually bringing out to people. So if you put a probabilistic model over that, then you should be good. So hopefully that that answers the question. From Ron Borland, so this would work by sticking private over your data and then allowing it to be available. Yeah, so that's the idea. So so you would have your data set that you've collected, that might be survey data or whatever, and then you would instead of just providing that on a website somewhere and allowing people to download it, or having or restricting it so there's only a small set of people who have access. What you would do is you would put that onto a server, you put private over the top of it, and then people would be given access to private in order to be able to run the analyses. And then they would program up those analyses, and that would give you the option of doing that without being so concerned about what was being released. So yeah, exactly, that's how you would do it. Okay, can you point me to any research publication, white paper related to this? Our team is planning to do a literature review on a certain topic, and this could be a good example of an application domain for that. We would like to read up further and cite it in our paper. Yeah, so perhaps what I'll do is I'll send you a set of references. So the main language itself hasn't been written up in a publication as yet, but there are some associated papers that I can point you to, as well as some blog posts and so forth that go into some more detail. Okay, excellent. So it looks like that's all of the questions. Are there any remaining questions before we finish off? No. Okay. Cool. So we'll leave it there for today. Thanks all for coming, and again, sign up for the workshop if you're interested in learning more in a hands-on fashion about how to use Private. Okay, thanks all. See you later.